Today I'm going to introduce our paper, which is titled as Meta Policy Learning for Cold Start Conversational Recommendation. My name is Zheng Dongchu, and currently I'm a PhD student at the University of Virginia. So this is outline of today's talk that I will first briefly introduce our motivation, and then I will go through our solution, which is named as Meta CRS in detail. And in the end, I will show some experimental results on 3 public datasets. So to begin with, I want to briefly introduce conversational recommendation system. So conversational recommendation provides personalized recommendations through interactions with users by asking questions to explicitly elicit preferences and also make recommendations accordingly. However, the cold start problem also exists in conversational recommendation. For example, given a CRS system trained on a group of Chinese food lovers, the CRS system may learn to ask questions about Chinese food and can effectively elicit user preference. However, when a new user comes and she doesn't like Chinese food, the current CRS system will be ineffective to ask her a preference, since the questions or the conversation strategy will still be about Chinese food. So this motivates us to develop methods. Basically, we argue that a single CRS policy or a single CRS agent is non-optimal for all the users. So to deal with it, we propose to learn user-specific CRS systems for each user. However, the challenge is the tolerance of users is limited, which means we have limited budget to do conversations with users and to learn their user-specific policy. And also the current coupled CRS agent do exploration and exploitation at the same time, and they are ineffective to explore the user preference for fast adaptation. So, based on the motivation, we propose our solution, which is named as Meta CRS. Basically, we learn a Meta CRS policy over existing users for fast adaptation on new users. Specifically, we identify user preference with a meta exploration policy to facilitate fast adaptation in the adaptation stage. And also, we adapt both conversation and recommendation components to improve the overall performance of the CRS system. So, let's go into the methodology part. So currently, also a lot of research has formulated the conversation system as a reinforcement learning problem, as the CRS agent is required to make optimal actions according to the current state. And the formulation is as follows. And specifically, we interested in the meta reinforcement learning problem in conversational recommendation, since that due to the difference of user preferences, the user's response to the questions will be different, which impose the user-specific reward function. So, in this scenario, a single policy is non-optimal for all the users, since the environments, which is essentially the user, are different because the reward function are different. So instead, we propose to optimize the following user-specific loss function to maximize the reward or the returns of each user. So specifically, we have when we do the learning, we have a small subset, which is essentially several conversations to conduct with the users, and we do the policy adaptation to obtain the user-specific policy, and then we will evaluate the adapted policy on a small query set. And so this is our framework. Our work has 3 major components. The first one is exploration stage. basically we learn a meta exploration policy to elicit the user preferences. And in the second conversational recommendation stage, we will choose a fast adaptation of the CRS policy. And based on the explored user preference in the exploration stage. And we also propose a state-aware item recommender, which is also adapted with the CRS policy to improve the recommendation quality. And in the end, we propose a transformer-based state encoder to encode both positive and negative feedbacks during the conversation. So the meta exploration policy is trained by the design the exploration reward. So intuitively, a good exploration policy should help us identify preferences for all the users. And we train the meta exploration policy on all the training users. And we assume that the testing users also sampled from the same user distribution. So the meta exploration policy is also expected to effectively identify user preference for the new users. And to facilitate this, we use existing embedding of the training users, which can obtain from historical recommendation data. But we do not require the embeddings of the users during the testing. And in the second stage, which is conversational recommendation stage, we will simply update the model, the policy according to the user-specific reward function. And we want to maximize the returns for each user. Specifically, we use GRU to keep track of the conversation history. And at each time step, the output of the GRU is input into the policy to keep track of the conversation. And also, as shown here, that the hidden state of the exploration policy is inherited by the user-specific policy. And the hidden state of the meta exploration policy can be seen as the user-specific information, and we will conduct our fast adaptation based on the explored user information. And also, we propose a state-aware item encoder recommender. Basically, this is its form, and we train it by using the hindsight loss function. The intuition is that once the target item is reached, we can use a signal to improve the ranking quality, and the target item is reflects the preference of the user. So we can use the signal to improve the to obtain the user-specific item recommender. And we also propose a transformer-based state encoder to encode both positive and negative feedback. And basically, we propose we use we will aggregate the item encoding and use a transformer to calculate the feature interactions between the positive and negative feedback. And in the end, we will obtain the state embedding based on the current state conversation history. So this is our overall optimization algorithm. Basically, so the optimization algorithm have a local adaptation stage, which is the inner loop, and also have an outer loop. So in the inner loop, we will conduct local adaptation to update the policy and the item recommender. And also in the outer loop, we will update all the parameters to maximize the performance on the query set. And when testing, we only do the local adaptation, where we adapt existing CRS policy, adapt the meta CRS policy to user-specific policies, and then we will evaluate adapted CRS policy on the query set. So in the experiments, we follow the reward settings in the Pioneer CRS paper, which is EAR, and we also we design a user simulator to simulate the user feedback. So for more details, you can find them in our paper. And we consider 3 public datasets. So basically, in the experiments, we try to answer the following 4 research questions. Basically, whether our method can beat the state-of-the-art methods, and does our meta-reinforcement learning-based adaptation strategy can work better than other adaptation strategies. So we consider 2 kinds of CRS baselines. The first group of baselines are state-of-the-art CRS baselines, and the second group of baselines can handle new users by updating the user embeddings. We also consider 2 simple adaptation strategy. The first one is fine-tuning, and we also consider independent adaptation. Both of them are not designed for generalization. So yeah. And so this is the main result of our paper, that so the key takeaway here is that from the results of group 1, we can conclude that a single global policy cannot handle new users effectively, and their performance is much worse than the second group and also meta-CRS. And also, adaptation recommendation is helpful. By updating the user preferences for the new users, we can see that the performance in group 2 is generally better than group 1. And in the end, we conclude that meta-CRS not only better than group 2, but also better than simple adaptation strategies, fine-tuning, and independent adaptation. And in the ablation study, we studied that the influence of the size of support set. We can see that with small conversation budget, the performance of meta-CRS increased significantly. And yeah, we also conduct ablation studies to show the proposed effectiveness of the proposed components. And we also show the case study that you can see that in the first figure, that meta-CRS learns to ask user-specific questions and make a successful recommendation early. And the meta policy and the strongest baseline FPAN cannot do that. So key takeaway of this paper is that when you want to learn user-specific policy, do not train a user-specific policy from scratch. Use meta-CRS, and we propose a dedicated meta-exploration policy to identify user preferences, and also an adaptive item recommender to improve the general recommendation quality. And we also propose a transformer-based conversation history encoder to encode both positive and negative feedbacks during the conversation. And we also publish our implementation and data on GitHub. And this work was supported by the following 2 fundings. And thanks.